Good morning, everybody. My name is Irene Chiesa and I am a PhD student at the University of Pisa in Italy. Today, I will talk to you about the development of sutureless clips for intestinal anastomosis. Nowadays, manual suturing is the current gold standard for intestinal anastomosis. It is a technically challenging and time-consuming procedure that requires a learning path for the surgeons. In addition, it has a high probability to failure that can also lead to the death of the patient. In order to overcome these issues, we developed and fabricated smart sutureless clips for intestinal anastomosis. The rationale of our device relies on the negative expansion coefficient of regenerated silk. To fabricate this innovative device, we exploited 4D printing. 4D printing is an emerging and innovative fabrication technology that denotes the fabrication via additive manufacturing of structures with the capability to shape-transform over time in a programmable way and under the application of external stimuli. Therefore, the main features of 4D printing are smart materials, 3D printing technologies, and external stimuli. In this study, as biomaterial inks, we used regenerative silk, that is a thermoresponsive, thermoplastic and piezoelectric polymer, and PHPV, that is biocompatible, bioresorbable, and has enhanced mechanical properties that are comparable with the ones of petrochemical polymers. Our device is made of a bilayer alloy tube comprising a first layer of PHPV and a second layer of silk compound. Two different silk compounds were explored. The first one comprises calcium chloride, whereas in the second one both calcium chloride and potassium nitrate were added. The device was fabricated via extrusion-based 4D printing, equipping the printer with a rotating spindle. Here there are some photos of the developed devices with different regenerative silk compound. Microscopic images revealed the bilayer structure of the device with a thickness of around 50 microns. Then the tubes were characterized by FTIR, before and after conditioning at 37 degrees and 90% of relative humidity. The analysis revealed that the addition of potassium nitrate increased the amount of beta sheet. This is due to the increased salt presence that acts as a cross-linking agent. Differently, the treatment in the climatic chamber slightly decreased the amount of beta sheet. Then mechanical compression tests were performed, and in accordance with the result, the tube comprising potassium nitrate has a higher ultimated tensile stress and compression elastic modulus. This is due to the higher content of beta sheets that increase the structure collapsing resistance. Then finite element modeling were performed in COLSOL multiphysics in order to analyze the capability of the developed tube to contract under thermal stimuli and compress the intestine wall. A solid mechanics module in stationary condition was used, and more in details for the tube that is composed of two layers, a linear elastic material module with the addition of the thermal expansion module was used. Differently, for the intestine wall, only the linear elastic material module was implemented. The rationale of our device relies on the negative thermal expansion coefficient of regenerated silk that is higher in modulus if compared to the one of PHPV. In addition, when potassium nitrite is added to the solution, the Young modulus of the regenerated silk increased and overcome the one of PHPV. The models reveal that the tubes is able to contract and compress the intestine wall when the temperature moves from the room temperature to 37 degrees, that is the temperature inside the human body. In addition to that, in accordance with the results of tear and mechanical tests, when potassium nitrate is added to the solution, the compression is higher. Finally, ex vivo tests were performed on a porcine intestine, comparing the burst impression of a pristine intestine, a conventionally sutured intestine, and intestine sealed with our device. As you can see from this slide, the burst impression of an intestine sutured with our device increased if compared with the one of conventionally sutured intestine, and is comparable with the pristine one. To conclude, in this study, bilayer tubes made of HBV and regenerated silk were successfully fabricated by extrusion-based 4D printing. The addition of potassium nitrate to the solution promotes the formation of beta sheets, thus stabilizing the structure and enhancing its resistance to collapse. Finite element simulation and ex vivo tests were performed and proved the potential of the developed 4D printed bilayer tube as a bio-based device for intestinal anastomosis. In the future, in vivo tests will be performed in a murine model to test the capability of the device in vivo. And in addition, complex regenerated silk pattern deposition will be explored in order to maximize the compression behavior. This study was partially financed by the Italian Ministry of Education under the PRIM project vision. I thank you for your attention, and I will be glad to answer all your questions.